recording for whoever can't make it, and that seems to be working, which is good. And then we'll be on our way. Before getting too far, a couple quick administrative notes. Oh, actually, I should probably get the attendance sent out. I nearly forgot about that. So, while I get the attendance thing pulled up, which I could have been doing when I was sitting here, the little admin notes, I guess, to start with are, first of all, a reminder about the AGM, which is happening somewhat soon. So, our AGM is going to be in April for the Society, and during that, you can run to be part of the committee. I'll probably put together a little Google form for that, since it seems like I like doing Google forms. And that'll just ask, hey, are you interested in running for some position on committee? There's a whole bunch of different things that you can do. It's pretty chill. You only have to dedicate an hour a week or something to come to the meetings, and then a little bit of extra time depending on what your role is, I guess. But I would highly encourage people to run for some position on the Bionics committee. I'll have more details about that to you very soon. Nice. The other thing is that because, as was pointed out, this being a tough but pretty good period, surviving anyways, I've been very busy trying to write up these things after the sessions as well. So that way there's a written version of these machine learning sessions, especially for people next year. For whoever takes on my role of leading Bootcamp, they're probably going to want some sort of material to work from. So that would be helpful. So I'm in the process of writing that up. It might be a little bit longer than normal, but I will have out, just like I did last time, the recording. And I'll just send that recording, the link to it, directly on the Bootcamp channel on Discord, so that people can find it there. And failing that, it's also on our YouTube channel for Bionics, so you can always find the recordings there. Excellent. Okay, with that out of the way, then I will find the attendance sheet. That took me far too long to find, and I will send this link to you real quick. As always, this little attendance thing is just for keeping track of how many people we have showing up usually, and we can use that information to squeeze money out of people for funding and stuff from the university. So definitely fill that out. Just put in whatever name, as long as it's somewhat consistent from week to week, and then we can be on our way. Awesome. So I'll start with a little poll, if nothing else, to make sure that everyone's alive. So let's see if I remember how to do polls. Have you done? Or let's see. Do you know anything about neural networks already? And I'll ask that so I have an idea. And that's a poll in the Discord. So I have an idea of how many people have a little bit of experience, how many people it's really new to, so I can figure out how much time to spend on what, which should be useful. Dun, 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 dun. Oh, lovely. We've made it way over here to a different window. Oh, and we found a chess game that I'm busy losing. Wonderful. Here we are. Cool. Nice. So our poll has a couple of shrugs, one person who knows a bit about things, and one person who doesn't yet. So that's fantastic. We have a good mix. Cool. So on that note then, to kind of catch everyone up to speed a little bit, we'll talk about briefly the basic idea of a neural network and how they work to help computers learn, and then we'll dive into some actual writing of code in Tensorflow again, and we can build on the data that we processed last week. So I'm probably just going to be skimming through articles, using them mostly for their diagrams, since I didn't have time to steal their diagrams for slides. But if you have any questions along the way, just let me know, and I will also be including all of these links in the eventual write-up I do, and I'll probably put them on the Bootcamp channel when the recording goes up as well. So that way you don't have to re-find all of them. Excellent. Okay, so what are neural networks? Like all machine learning algorithms, they are mathematical constructs, basically, that transform some sort of input into some sort of output and try and do that intelligently. The intelligent part doesn't necessarily come from the single neurons, as this is a single neuron here, and I'll talk about what this means in a second. But instead, it comes from combining these neurons in a way that forms a network so that they can capture more complex relationships. Like here, for example, would be an example of a very, very simple neural network, but something that's complex enough to solve this basic problem. In this article, we have two input neurons, and those feed together so that every neuron on the first layer feeds to every neuron on the second layer, and so on. Those are called dense networks, and we'll see a little bit more of them in a minute. But neurons, how do those work? As it says, they're taking inputs, doing some math, and producing one output. So they're pretty simple. And the things to remember are that all these variables here, all this is just numbers. So in our case, those would be like the values from our EMG thing. Those would come in, and out would pop some classification eventually, out of our whole network, that is. So what you usually do with each neuron is it takes some input, which is one number, and it multiplies it by another number. That one's called a weight, so here you can see the equation for that. You have your x, which is the input, and then your weight, which is this w, and you multiply those together. You add up both of these values, the x1 and the x2, once you multiply them here, and then you add this last little term called a bias, and that gives you your output. The idea of these weights is they can be negative or positive numbers, and that tells you how much this input should influence the output. So it allows different inputs to change your output. But say if your output is really rare, you don't want to actually output a high number there very often, then you also have this bias term, which is this b, and that's just a constant for the particular neuron that can also be updated via the training, which we'll see in a minute. But it can use that to compute some sort of output. So at its core, what most neural networks do is they take some inputs, they multiply them by some weights, then they add some number to it, and that's their output. So they're pretty simple overall. The last thing that you do after you calculate this is you can pass it through some sort of activation function. So what this activation function does is usually take that output. So you can imagine if you just have two values being multiplied by each other, summing those plus a bias, that could be a really big number or a really small number. So you could have things up in the thousands. And the bigger problem with this, I guess, is if you think about your data, if you're using really big numbers, even if the big numbers don't mean, even if the big numbers aren't the most important numbers, they'll dominate because you'll just have a really large sum in the end. And that can kind of compound to create some big numbers that stop carrying meaning, I guess. So what happens is you pass them through an activation function. These activation functions here can be a whole bunch of different things. We'll be talking about at least 3 of them today. And here is a nice commonly used one, like they've said. This is one of the simplest ones. This is the sigmoid activation function. So just like in maths, your x here is your independent variable, so that's your input. In our case, our x-axis is the output of this equation up here, the xw1 plus the xw2 plus the b. That's what this x part is here. But you can see, no matter how big or small your output from this neuron is, your final output will always be between 0, which is just down here, and 1. And that's just the nature of this sigmoid function in particular. So that guarantees that no matter what you put it into your network, you'll always get something between 0 and 1 out. So it's nice and sensible. I don't entirely know. There we are. How I zoomed into that. Cool. All right, so this article then goes on, talks about, yeah, here are some real numbers. That's kind of useful, I guess. So assume you have a 2-input neuron. So that's just like what we saw above. That is this here. This has 3 parameters. Because remember, the x's are inputs, so they're not something that's stored in the neuron. But instead, the neuron has its weights, and it has one of those for each input. So it has 2 weights, w1 and w2, and then this bias here at the end. So if we take a look at how that is actually calculated, then down here, we can find the answer. So here you are. Take your weights, which actually, here I'll show if I can click off of this. Does it let me click off of this? Please. Oh, that's very strange. Okay, I click way over there. So yes, these weights here, we're just hypothetically saying those to be 0 and 1, and then our bias is going to be 4. Then what you do is you take your first input, multiply by your first weight, so that is 0, and in this case our input is 2. So you take 0 and 2, that's going to be 0, then you add to that 1 times 3, because your second weight is 1, and your input is 3. Then you add on your 4, so your output is 7. You run it through Sigmoid, the Sigmoid function, and as you can see, it's a really close number to 1, because 7 would be really far off this graph this way, over here. So just about at 1. That's the basic idea. You may be wondering how it does anything terribly clever with that, but that comes from the emergent properties of combining lots of these different neurons. So in a real neural network, here we have 3 parameters. At the end of this one, there's more than that, but not a massive number since this is just learning the basics. In the neural networks like that we'll be dealing with today, the number of parameters we have isn't 3. It's more like, I think, 31,000 is one of them, and one of them is about 18,000. So many more numbers involved. And that's where lots of the complexity can come from. And you also obviously have inputs that are more than just 2 little inputs. In our case, we have 8 inputs because there were 8 EMG channels, but also then 118 long, I believe, is what we're at the moment. So that's a lot of data that we're feeding into the networks. Then this tutorial is nice. It goes on and shows you how to code your own things. We don't need to do that. And in fact, you probably don't need to ever unless you want to learn it. Learning it is good, but TensorFlow does all of this for us, which is nice. Here's an example of what the neural network would look like I said earlier, where you have your input neurons. Each one of these circles is 1 neuron, so those have 3 parameters each. So I guess if there's 5 here, then you'll have 15 total parameters in this network, instead of the 31,000 we'll have later today. And this is just walking through different examples of how the network works. So basically, it works as the lines would imply. So say from, these are your inputs. So say from H1, say if H1 is the neuron that we simulated up here, the output of H1 will be 0.999. So then it will feed 0.999 this way down to this output layer, and that'll become the first input of the output layer. So that becomes the X here at the output layer. And then it will go along, and this neuron will have some different weights. This will calculate a different number that'll be fed in as the other input, and you'll finally get some output answer. So you can chain these arbitrarily deep as much as you want. And in fact, the deeper they are, usually the more connections you can record, or I guess predict. Awesome. Yep, so this is talking about how you can code that bit where you're feeding things forward. Again, we won't need to do that today, which is good. And training, this is a bit of a tricky part. So I won't go over exactly how the whole maths of this works because it involves partial derivatives, so it's like multi-variable calculus. If you're curious, definitely look into it. This tutorial does a decent job of explaining it, though you have to do a bit of the maths as well on your own. But the idea is, if you're training this network, here's some example data they have. So here they've normalized the weight and the height of these people, and our goal is to predict whether they are male or female based on their weight and height, I guess. So you can see we've normalized the data, so this is like a pre-processing step that gets it all down to numbers. We've already done that pre-processing. So then you can imagine what happens is then you're feeding in these 2 numbers, a weight and a height, as your 2 inputs, you can see here. And then out comes on the other end either a 1 or a 0 representing the gender for male or female. Cool. But a way, or before I guess we can train the network as it says here, you need a way of assessing how good your network is already. So, for example, how do you, it's a bit intuitive, I guess. If you just ran it with, say, Alice, and it output a 0, well, that's just the wrong answer. We're looking for a 1. But how do you classify, or quantify, rather, when you're getting closer to the correct answer? The answer is there are a bunch of ways. The one used in this tutorial is just mean squared error, which you've probably seen if you've done statistics before. But the idea is it takes a look at these, which are all of the true values, these ones and zeros, and takes a look at the output of the neural network, which is what the y predicted would be, and finds the mean squared error, which is a measurement you can think of how far away all of your points are from all of the points where they should be. So again, they go through that a bit in detail, which is nice. Here's the loss calculation, for example. So yes, so if you predicted 0 for all of the outputs, for example, well, that's correct for the two males, because 0 represents male, but for the two females, that's wrong. So you can see here's our y true minus y predicted squared, and if you add all that up with the mean squared equation, then you'll get a loss of half. So that means you're like halfway there to having this fully correctly classifying people, I guess. So here's an example of how you can do it. And then here's the training part that involves the actual multivariable calculus. So don't worry too much about this. Again, you never have to deal with it in TensorFlow, which is really nice. But if you are curious how neural networks actually manage to improve over time, is since the loss is just a mathematical function, and all of the neurons can be represented as mathematical functions, what you do is you can go for the loss equation and calculate different partial derivatives. And partial derivatives, if you haven't dealt with them too much before, it's just saying for this loss function, which has a lot of variables involved. You can see here are all of the weights and biases in our entire network. For all of these, what is, or if we were to change one of them, for example, so let's see, where do we start with? They're starting with weight 1, it looks like. So if you want to find how you want to tweak weight 1, then you can go through this function and find the partial derivative with respect to that weight 1, and that will tell you if you change weight 1, how that will affect the loss. Then what you do is, since you know if increasing that or decreasing that makes the loss bigger or smaller, you want to reduce the loss, so then you just take a step kind of down the gradient, down the loss function's gradient, so you're moving towards a smaller amount of loss, and then when you run your whole network the next time, your answer will be closer because your loss has been reduced because you've tweaked this variable in the correct direction. So here's the bunch of maths on it. Like I said, we won't dwell too much on all of this. It's a bunch of calculus if you are interested. It's pretty cool. There are some good explanations of it. 3 Blue, 1 Brown does some good videos on machine learning. If you've not come across their channel before, I'll put that in the links. Lovely. There's us calculating derivatives there. So there we are. Once you're done with the whole calculation, which again, remember this will be done automatically for you by TensorFlow, you get something like this number here, which is 0.0214. So it's really small, but this is like a slope or the gradient. If you changed weight 1, how it would affect the loss. So here, it's a positive number, which means if we increased weight 1, it would make our loss bigger. But we don't want our loss to be bigger. We want our loss to be smaller, because remember, the loss is our measurement of error. And if we get to 0 error, then our network is working perfectly, which is very hard to do, but you can get very close. So since they're proportionally related, I guess, what we want to do is decrease weight 1. So if weight 1 gets smaller, our loss will get smaller. And when you do that update, you multiply it by this value here, nu. And nu is just the learning rate, which controls how fast you train. If you make it too big, you'll sometimes miss the optimal point. If you make it too small, it'll just take ages for your network to learn. It'll be a really slow learner. But here you can see exactly what I described a second ago, where you have the weight. The new weight is the current weight, and then you're subtracting however fast you want to learn multiplied by this gradient, which here is a positive number. And if that switches directions, either way, L is decreased. So your loss will lower. Excellent. Okay, I think that's the extent of what I want to go through on this basic thing here. And I realized that was a lot of incredibly abstract stuff to start off with. So I'm going to do a quick poll and have anyone ask questions. And there are no questions too general to ask at this point, because that was a very general overview. So, how are people about the idea of neural networks. Neural networks you'll sometimes see described as NN for neural network, because they are modeled after neurons. Very neat. Okay, well, that's more positive than I was expecting. I felt very waffly on my end, so I'm glad that passed along decently. That, or you're all just looking to move on to the next bit, which I wouldn't blame you for. Okay, awesome, cool, got some good feedback there. So, with that in mind, this is the basic idea of a neural network, but there are so many different types, and they get incredibly complex. That's why we have people who, get PhDs in machine learning. With that in mind, then, we have two different types of neural networks that we could look at next. Which would you like to look at? The options are a convolutional neural network, so a CNN. That's often used for lots of image things. Or we have LSTMs, which is long short-term memory. If long short-term sounds dumb to you, it sounds dumb to me too, but I didn't invent it. But yes, so those are our two different models. Does anyone have a preference which we take a look at first? Anyone you're curious about? Convolutional neural networks or LSTMs? Long short-term memory? Convolutional sounds cool. Nice. I think it sounds cool too, so we'll take a look at that one. We'll do both of them anyways, but we'll look at that one first. Cool. So, yet another excellent resource that I'm going to steal the diagrams of and ignore most of the words. But you can, of course, go and read it at some point when you would like. So, what convolutional neural networks are really good at doing is looking over large data sets, but looking at them in the same place everywhere, I guess, if that makes sense. So if you imagine a network like this one, which is just a simple feed-forward network, but we wanted to do something like image recognition, so look at a picture, which is what convolutional neural networks are really good at. If you want to look at a picture, every single pixel, if you think about it, if you want to do color images anyways, has three different values. You have your red value, your green value, and your blue value. And then if you have a big image, say your image is 300 by 300, that makes for, quick maths, is that 900,000 pixels in a 300 by 300 image? Yep, I think so. Maybe not, just kidding, 90,000. Regardless, lots of pixels. And each one of those pixels has three additional values as well. So if you think about the number of input layers that you would need, and we'll pop up so I don't lie to you a third time. That was not, in fact, a calculator. Calculator. So if we then take something like a 300 by 300 image, you have 300 times 300 times 3 for colors. If you had an image with transparency, you sometimes have a transparency channel, so you'd have up to 4. But we'll go with just colors. So you'd have something like, so it was 90,000. Yeah, so you'd have 27,000 input neurons. And if you think about that, 27,000 input neurons means, because each neuron has, well, at least 3 inputs. But the way that these work is in dense networks anyways. Like this H here, the hidden layer. This neuron would be connected to every single one of the inputs. So that means every one of these individual neurons in this middle layer will have this many plus 1 different values stored in it. So that's already way more than both the models we'll be using today. So that's 27,000 parameters for one neuron looking at a 300 by 300 image. That gets unsustainable incredibly quickly. If you want something like, 100 neuron layer and then 3 of those layers, you end up with 81 million different numbers that you have to keep track of. So that's obviously unsustainable. So how do convolutional neural networks solve that problem? Well, what they do is, let's see if I can find the image I am looking for. Excellent. They look at only a window of the image at a time, and they kind of slide over it. So to make that make a bit more sense, I can actually look at this excellent animation they have here. Can you all see this animation decently? In fact, I can probably pause its animating for a moment. Yes, excellent. Can you all see that? Is it big enough and understandable? Excellent, fantastic. You've zoomed in, it looks fine. Good. Cool. Okay, so imagine then that we have some image. This image is really small. In this case, our image will just be 5 by 5 pixels. So that's like something hilariously tiny here. But you can imagine each one of these numbers being an intensity for how bright that particular color is. This first block here could be your red, and you could have your green, and then you could have your blue down here. So what these convolutional neural networks do is they have these little filters, and these filters are the same shape as the little input that they're being scanned over. And the way that these work is very similar to what we looked at a second ago with our initial neural networks, where you take all of these input numbers, so think of these as all of our x's, so those are our inputs, and then you have all of your weights, which here are also labeled again with the W, and you go place by place and multiply them together. So here, for example, you're taking this -1, you're multiplying it by 0, so that's just going to be 0. In fact, all of these ones around the edge will be 0, because those are 0 there. And then on the inside, you'd have 1 and -1, so you'd have -1 there. Then you'd have 2 and -1, so you're at -3 now, and these other two ones are 0, so we can ignore those. So this filter will output -3. Then you can repeat that process for this one down here on that same input, and then this one down here on that input. So you can have unique filters for each color, if you will. So if this is a red and a blue, or a red and a green and a blue, this would be a red and a green and a blue. Then you add your bias on the end, so you still have that B term. The only big difference, I guess, is that our input is now two-dimensional. You have these two-dimensional weights instead of our one-dimensional ones from our first example. And then what happens after you add all of those up, you'll get something that computes to -6, and then your -6 gets put into this little output here. So you can see as this goes over the input, in fact, it's here jumping by 2, so we'll talk about why that is in just a moment. So it's generating this output here, and you can see as it generates the output, there are 2 different types of filters, so you can get some features with this first filter, and some different ones with the second filter. And it kind of scans over it like this, which is a cool little approach. So the reason we do that, and I'll fly back up a little bit here. There we are. So there's your traditional network. That gets to be too many, as we talked about a minute ago, like too many connections, too many things to keep track of. So instead what you have is convolutional neural networks that transform a volume of inputs. Now the reason this is a volume is because if you think about it, even two-dimensional images on your computer are three-dimensional in terms of data, because color is the third dimension. So you have like your width, your height, width, height, and then color is this depth bit. That's sometimes why it's called color depth. But then what happens is your convolutional neural network can go over this volume and generate outputs here in the middle, and it can do that over and over and over again until you get a small set of features that you are interested in. And that could be just like a classification of the image. So this could be like a set of things for the probability that it's a car, probability that it's looking at a cat, probability it's looking at a dog, something like that. So let's see, here's an example of a particular convolutional neural network that's meant to figure out, classify images. So the first convolution, when it scans over, it'll actually generate something you can almost kind of see an image in that output volume there. We'll talk about ReLU in a minute, as well as pool. And then at the end, what FC stands for is fully connected. So that's one of these dense layers here. So you take your outputs at the very end, then now, since, say, at your end, you've managed to reduce this large, massive red volume down to just this smaller green one, now it's much more reasonable to do what we did over here and just make every value in that green thing an input to an X and have a regular neural network just like this. And so that's how it's eventually then coming up with classifications. And what we'll be doing today, I realize this is still quite abstract, but we'll get there. What we'll be doing today is classifying EMG data, which we can treat a little bit like images almost, into these different categories, just like is happening here. So we'll be using a similar architecture to this, except probably with fewer layers. Awesome. So the different layers. There is the convolutional layer, which is the one that we got to see down here. Way down here. This one. So this is the convolutional network. The process of convolution, by the way, is running a filter, like these filters here, over some input like this. So this is the convolution process. That's why they're called convolutional neural networks. And then they're generating these outputs over here. So the other layers involved that aren't just the convolutional layer, for example, like the ReLU layer, that's an activation function, actually. So earlier we saw the sigmoid activation function, which is this guy here. And this keeps everything between 0 and 1. It's very nice if you're dealing with like probabilities, because 1 would be, oh, it will certainly happen, 0 will be, it certainly won't happen. You have a nice sliding scale. But what has been found, especially in convolutional neural networks and also in some other ones, is if you change this function out for something different, like a rectified linear unit, which is what a ReLU is, you can get much better performance. And like both in terms of how long it takes to train, it'll train faster. Let me see if I can just find the graph, please. There we are. It'll both train faster and be give you generally better results, because it's valuable in some neural networks to have pure 0 values. So what the ReLU function is it's just y equals x for values greater than 0. So here it's just a linear line, totally linear relationship with a gradient of 1. But once you hit 0, it just stays at 0, so you can't get any negative values out of it. So this allows it to capture some relationships that aren't strictly linear, but it still keeps the calculating of like those gradients that I talked about with all that calculus bit. It still keeps the calculation of those easy, because if the value is less than 0, you don't have to calculate any gradient to send through. It's just 0. But if it's greater than that, it's very simple to find the derivative of this, because it's just 1, because it's just the gradient. So these are a common activation function. So when you see ReLU, this is what they look like. And they're good for high performance networks in terms of like they train very quickly. But with some networks, like recurrent ones, which we'll deal with in a little bit, which are Lstms, are a type of recurrent network, these can cause issues. So we'll look at that in TensorFlow in a bit. So what's happening here then is you're going over the convolution thing. So here you're getting, a whole bunch of different values. ReLU is getting rid of anything that's less than 0. So that filters out anything less than 0. So that's your activation function. Here we have another convolutional layer and another ReLU. And what pool layers do, there are a couple different types of pooling. I wonder if they have bits about pooling. Sure do. Excellent. So how pooling works is it's a little bit like a convolutional approach, except you aren't doing many calculations. The point of pooling is to shrink your image, so you have fewer things, but you're doing that by discarding information as opposed to like processing it. This is sometimes good, because if you design a neural network that processes every last little detail, you can sometimes build models that are so powerful they'll just memorize the data you give them, and that's something called overfitting, because if they memorize the data you give them, they're not really learning the general connections between things. So if you show them some data they've never seen before, they'll often struggle to classify it or predict what comes next, depending on the type of neural network. And that happens because of something called overfitting. And so this is a way of combating that by actually removing some information so that it can't fully just memorize the data set. You have to force it to understand it instead of memorize it. So how that works then, this is something called max pooling. So you just take the biggest number in your filter size, and also the stride determines how far each one of these filters moves. So we'll talk about stride in just a moment. But the idea here is this is your input, and then to transform it to your output, you just take a look at, well, here's this quadrant, take the biggest number, that's the output. So 6 goes over there. Same here, 8's the biggest, that goes there. 4 is the biggest, it ends up in the output, and 3 is the biggest, and that ends up in the output. So you've managed to shrink your image, you've discarded a bit of information, but the idea, the way this works often, is because Your most important information might also be the biggest numbers, for example. So if you have really important information, if a feature is showing up really strongly, you have like a big number here, that'll always get passed through. And then all the little tiny like details, those don't matter as much, so they get tossed out. So that's how these pooling layers work. And that can help simplify the model. Let's see, there we are. Yep, so you can see it kind of removes some information, but keeps just the important bits. And then you just repeat this process for this particular algorithm. Ours will be a bit simpler than this. So I think the last thing then to touch on is probably striding and how you stride over these things. So yeah, here's an example. Yeah, we'll go over that last. So here is the difference of the difference that a stride makes. So if you can imagine this being our input, we're now doing something one-dimensional instead of two-dimensional. But our filter size would be 3, so that's the area of this image. There are some air quotes here because this is one-dimensional. You could have, I suppose, a one-dimensional image of something. But the idea is that this neuron, or this filter rather, is looking at these 3 things, so I can look at all 3 of those and process them. The one right next to it overlaps with 2 of them, so I can process this item, and this item, and this item, and so on. So this is this is a stride of 1. You're sliding your filters along one at a time, because you're going from here, then just one over, then just one over, because you're, just moving from this is your first thing you're calculating to that's your first one, that's your first one, kind of thing. Here is a stride of 2, I think. Yep. Because you can see here, your first line goes from 0 to the neuron. But now, for the next neuron, you start at 2 and then go up there. So that's a jump of 1, 2 over. The reason for doing these strides is because you can still sometimes get some like overlapping information. For example, this 2 here is still read by both of these outputs. It influences both of them. But also this actually shrinks your output size. So this is kind of like a pooling layer in that it creates a smaller output than the input you put in. Except this also has the benefit of doing some computation with it. So it's not just as simple as tossing out, any small values. So that is why down here in our nice animated version, it says actually at the top here, maybe? I actually don't know if it says exactly where its stride is. Yeah, but you can see, so that's talking about something different there. But the point is here that the stride is, and we can just tell by looking at it, that it is 2, because in your very first go, your top right corner, I guess, of the filter is obviously up in the top right corner of the input, but then you move over 2 things at a time, then you move down 2, and then 2. So that's why we're generating a smaller output than the input we've put in. Cool. The only last thing I think to touch on is the padding. You can imagine if your important detail, say you're trying to like identify a stop sign or something. So your stop sign is sitting here. You've got like the top of your stop sign. Here, I'll pause the movement. That's a bit distracting, isn't it? Go on. Pause. No? It has... Oh, there we are. Got it. Okay. So say you have your stop sign here. So here's the top of your stop sign. You can see my mouse, right? That's worth double checking, actually. My mouse is visible, yes? Excellent. Okay, cool. Yeah, so my mouse then here would be like the top of the stop sign. So say half of it is in the frame. So this blue part is the part that's actually in our image. So half of it's in the image. And then you've got, that stick that it's stuck into the ground with here for your stop sign. If you had a network that could identify stop signs really, really well, but what it was looking for was like, well, a bit of a curve, I guess, if you will, on this part of the filter. On the right side of the filter, it would look for a curve to the right. On the left side, it would look for a curve to the left. If you just started it, it's top right corner here at 1, then you might have a bit of an issue because the part of your filter, which again would be like this little crescent bit here that's looking for an edge, wouldn't be seeing the edge because the edge would be here. It'd be shifted over by 1. So it would have trouble identifying something at the edge of the pattern here. A way you can get around this with convolutional neural networks is just by adding on some padding. So here, there's 0 padding, so you've just put zeros all the way around on all sides. And what that means is that you can have the same number of strides, or sorry, you can do the same number of, or you can start your calculation up here in this corner, I guess, if you will. So in this particular example, it doesn't start here because it also starts up there. But if the stride here were 1, then you could start up in this corner at this 0, and then your curve here, of your stop sign, would be lined up with this curve detecting part of the filter right here. Even though it's only halfway in the image, you can still pick up on that half of it, so you can still identify things that are kind of like on the boundary, I guess, if that makes sense. And the padding type that TensorFlow uses that we'll be dealing with is something called same padding. So what that means is that if your stride is 1, so say if you're going over things just 1 at a time, it will guarantee that your output is the same size as your input. So if you think about here, all the places you can fit this 3x3 filter in the actual image, if you were doing a stride of 1, you could fit it here, and that square. You can move your square over by 1, so that's 2 places it can be, and you can move it over again, and you have 3 places it can be. So you can see there, if we didn't have the padding, we could have an output that is only 3 big. Now, granted, our output is 3 big, but that's because we're also doing a stride of 2. But you can imagine here if we added this padding, we had a stride of 1. So say we're starting up here, but then our second position for our top right corner is there, then there, then there, just moving over by 1 at a time. Then how that can work, you'd have 1 position for your square here, so that's 1 output, 2 outputs for that second position, 3, and then 4, and then 5. So you can see you can fit 5 filters onto it, and so you'd have an output that's 5 wide, and your input is 5 wide, so it can keep the same size. It prevents you from losing that edge information. Cool. That was a lot of waffle. I'll check in with people with a poll. So let's see, I need to remember to type poll. How are people feeling about CNNs? And any questions at all are excellent to ask, because I can probably answer specific questions better than I can waffle general things off, I reckon. So I have put the poll in the Discord. Feel free to type up a question in either chat, and I'll keep an eye on it. Cool. People seem to be feeling all right about these. Nice. Okay. I think then, if there are no questions, if you are writing a question, please continue to do so. If there aren't, we'll take a quick look at LSTMs, and we'll finally get to something practical, more hands-on. Actually writing some code and getting these models to do things for us. So, cool. If there are questions, definitely type them. Otherwise, I think we'll talk real briefly about LSTMs. So, lovely. Hopefully that's good. Nice. This is a wonderful article about LSTMs. I'm sure you'll see this all over the internet if you ever Google LSTMs. So if you forget this and you Google how do LSTMs work, you'll almost certainly get pointed back to this one person who did a really good post with a bunch of nice illustrations on it. But so we're gonna go over this. I'll do the same thing of just kind of taking a look at some of the pictures. So before, we were looking at 2 types of neural networks, these ones called feed-forward networks. In TensorFlow, it's called a dense layer. It's dense because every input is connected to every neuron, and every neuron is connected to every next neuron. Convolutional neural networks, called convolutional, obviously, because they perform this convolution operation, which is the process of moving a filter over an image. And then, that's really goodbye. LSTMs, long short-term memory, well, the memory part requires something a bit different, because if you think about the data flow, I guess, in both of these other neural networks, they're just turning an input into an output. That's all they're capable of doing. Data is flowing one direction. They can't remember anything. So as you know, the blog post starts, we don't think, or you don't start our thinking from scratch every second, but instead it's the previous information from previous things we've looked at that influences the future. So recurrent neural networks are structured a bit like this. So here, just so we can like translate our terminology, I guess, the x is now not necessarily one input value, but it is instead a vector. So this is like a list of values, a list of numbers. So here, our x in the LSTM article could be a vector that contains both of these inputs. So both of these inputs can be combined into one x here. H here is our output, so that would be our little output layer, just like that. That can have arbitrary different sizes. So you can see information flows from the inputs into the neuron, out to the output, but also the output of the neuron flows back into itself. And the way that works is it takes a look at the previous x, it remembers the last x it looked at, and when it's looking at the next time step, it compares, okay, here is this current time step, here is the information from the last time step, how do I combine both of these bits of information to generate a new output? And that new output then gets passed along for the next time the neuron has to calculate something. So that's how recurrent neural networks work. They have these loops in them, and that's how they remember things. These loops, and the way we'll be looking at them is unrolled. If you think about this, just kind of copy and paste this neuron setup here, put them all side by side, and instead of looping around, you lay the time axis out this way. So you can see x0 is at time 0, x1 is at time 1, x2 is at time 2, all the way up to time t. So you can have these loops, that's what they are at their heart, or at their core, but you can also unroll them, like this says here, and that's how this article will be drawing them, and it's just nice for thinking about things. It can even be good for performance if you have a small number of inputs. So that's a basic recurrent neural network. And they do really well, but one of the problems they have is remembering information over long periods of time. And so the way we deal with that is by changing. So yeah, here, for example, is they're talking about the issue is that these past inputs here that are pretty close by, you can sometimes use to calculate this, h here, because these output or these inputs, x0 is getting combined into the output of this neuron, x1 is combined into the output of this neuron, and both those outputs are eventually being chained up to the h3. But the farther those get away, the more difficult it is to connect the two bits of information. So what LSTMs do is have a bit of a different structure around them. So here is, like we were looking at just a moment ago, the standard recurrent neural network. The way this little terminology here works is the arrows are the flow of data. This is a tanh. So actually, I don't think I included the link for this, but we can take a look at it. This is another activation function. We won't be using this one today, but this is another activation function that neurons sometimes use. Please give me a larger image of that. That is such a small image. There we are, a beautiful tanh, hyperbolic tangent. So this might remind you of that sigma activation function that we saw in our introduction here. In fact, they look very similar, but the important thing to notice is that sigma's lowest value, or sigmoid's lowest value is 0, goes from 0 to 1. Hyperbolic tangent goes from -1 to +1. So you can have negative numbers as well as positive ones. So what this means here then in this little yellow box is there is a regular set of neurons. So in that box there is a neural network like we've seen before here. And its activation function instead of a sigmoid is a hyperbolic tangent. That's what that little yellow box means. So it's taking information from last time and information from this time, running it through that regular neural network, spitting out an answer, and then also feeding it forward to the next time step. Now what LSTMs do is greatly complicate that. And we'll dive through this. I won't do crazy amounts of details because this is a really well-written article, so if you're curious at how they work, then you can always take a look here, and it's also not vital to like what we'll be doing. But And in fact, I might just... Yeah, sure, I'll follow along with the article. So here's the terminology that we were talking about a minute ago. Like I said here, the yellow, that's a neural network layer. So these ones, that sigma sign there is short for sigmoid. So these output something between 0 and 1, 0 and 1, negative 1, and positive 1, and then 0 and 1 again. And then what all these red operations are, these are just point-wise ones. So this is just you're applying a function to the values. Here you're multiplying the values. So you're multiplying your two vectors. So that's like when you're taking your inputs multiplied by your weights. Here you're adding them. There you're running them through a tanh, but there are no, there's not a neural network here. So there's no weights or things to be learned at that step. And then, of course, when you split the errors, you're copying data. When you stick them together, you're concatenating data. So you're squishing the two inputs into one input, one bigger input. Awesome. So the core idea behind these LSTMs is they have this cell state. So you might have noticed there's now two inputs that feed from one thing to the next. This bottom input is actually just the output of this layer. You can see here they fork. So the output of this layer is being passed to the next one. That's just like our recurrent neural network here. We're forking one out and then also passing it forward in time. Fork one out, pass it forward in time. But this top bit is just a bit like a conveyor belt that starts at the first state and goes all the way along. This is its long-term memory. So that's where the long-term part of things comes from. And then it adds and removes information in different ways. So this first gate here, this sigmoid function, remember this will give you something between 0 and 1. And then you're multiplying that 0 and 1 thing by the information in your long-term memory. What this is a forget gate. So what this does is take a combination of the last output and this bit of input data. It thinks about, okay, what in my long-term memory is relevant? So say if you're looking at a sentence or something, and your input is, here's a full stop, we're changing sentences. You can get rid of information from the previous sentence. So this neural network will output some pattern that represents the old information as closer to 0, and the things that it wants to remember as closer to 1. And then it multiplies here, so anything multiplied by 0 gets forgotten. It's erased from this conveyor belt of state, but the other things are passed straight through. So that's how that first bit works. But then, after you've forgotten irrelevant information, you want to remember some new information. So here, this sigmoid is very similar to this one. It just basically decides how much of this new calculated information are we going to put into our long-term memory. So if you read some irrelevant detail, this will probably be a really low number, so it doesn't remember it. Don't need it in the future, just need it for this one output. But if it's something really, really important, then odds are that it will be passed through and remembered in the long-term state. So that's how this little one works. Here's another, it's a bit faint, but this multiplication here is the same as this one. It's letting stuff through or getting rid of it. And up here is just the addition. So this is taking the existing conveyor belt of information of your long-term memories, and we're adding to our long-term memories. That's how that one there works. Yep, so it's highlighting all that operations. And then finally, you have the information that you want to output. So what you can do is take your long-term memory, you run it through a tanh just to normalize it. There's not a neural network here, so it's not finding any new information. It's just reading the long-term memory. And then what this is doing is saying, okay, which parts of that long-term memory are relevant to this output? So from last time around, which is ht minus 1, and then this time around, so this word and like the previous words, from the combination of those two, what is relevant that we output? So if it's relevant, this sigmoid neural network will output a 1. If it's irrelevant, it'll output a 0. Then that happens, and it takes the memory, and it doesn't include the parts that are relevant, includes the parts that are relevant, and then outputs those both to the user and also to the next cell in the machine or in the memory network. So that's the basic conveyor belty process there. That is what a normal LSTM looks like. And that was a lot of word soup because it's a bit complex. And it takes a while for this to click as well. So if you come away from this session not fully understanding the details of these networks, That is fine. It took me ages to do so. The important vibe is feed-forward neural networks are good for finding connections between a small number of inputs and giving an output. Convolutional neural networks essentially do a feed-forward network kind of thing, except they only look at parts of the image at a time, and they do this in layers, looking at smaller and smaller parts, and kind of going up like a pyramid shape, so that you don't have to look at everything at once. You can get rid of irrelevant information, and you kind of build up like a pyramid. And here is kind of like that pyramid structure. So a big base, and you're kind of building up this sideways pyramid here, I guess. And there's your output that is just smaller than the input. So this is good for spatial information often. So finding like relationships in space. And then LSTMs are good for remembering things, because just remember the M is for memory. This allows you to remember stuff. It's good for time series data. So if you're thinking about, well, okay, this happened 5 minutes ago, something else happened 2 minutes ago, what's going to happen 1 minute into the future? That might be a good application for an LSTM or some sort of recurrent neural network. That's the only important bit to remember. It's just what each one of them are used for. Then you can always look up the details when you know that you have that kind of problem. There are also variants on it. I won't talk too much about these. I will talk a little bit about one that's quite popular, which is this one down here, the gated recurrent neural network, GRU. This one is also built into, a gated recurrent unit. That's also built into TensorFlow. This does a similar thing to the last LSTM, but it combines some stuff like the forgetting and remembering amount, for example. So this is a combined like update gate here. So it decides which information is relevant in the new stuff and what's relevant in the old stuff. But because there's a little negative one that just inverts things, everything that it forgets is equal to everything that it's remembering. Like, they're different numbers, but say if you're forgetting, if you're doing an English sentence and you're keeping track of, you know, the verb tense or something, and also, say, like, locations that you might have mentioned earlier, if you're updating the location, so if you get a new location, you're adding that here for sure, and you're also forgetting the old one simultaneously. So it's just like a bit of a simpler way of doing it as opposed to having two different gates. And you've also got some different connections here, which I could go through, but since we're not going over them today, I won't spend too much time doing that. But the idea is, these are like LSTMs. They're a little bit faster, sometimes work better, sometimes work worse, but are generally becoming very, very popular. So if you see GRU, or Gated Recurrent Unit, think LSTM, but tweaked a little bit. Awesome. Yeah, I was going to go over these today, but they're just so similar to LSTMs that it's not much different, especially in code. It's like a 3-letter difference. Awesome. Okay, with that done, that slog, I think it's time to finally move on to something interesting. Well, more interesting, maybe. More interactive, that's the one. How are people feeling about LSTMs? There we are. Nice little poll. Now is an excellent time to ask questions if you have any about any of this wild stuff. If there's any bit that you missed or got left behind on. Cool. Okay. Generally positive feedback there, so awesome. I'll give people just a moment to write questions, and in the meantime, we will... Hold on. Just for clarification. Why is a hyperbolic tangent used over a sigmoid function? That's a good idea. Or a good question, rather. Oh, you've also just left the meeting, or have you returned? It just said that you left. Let's see. Aha, okay, you've made it back. Excellent. Yes, that's a good question. Why the hyperbolic tangent is used instead of the sigmoid. The reason for that is sometimes you want to include, especially in this addition thing, you want to reduce, I guess, if you think about it, some part in your memory. So if your memory is a set of numbers that can be negative and positive, if you had a sigmoid here, you would only be ever capable of putting positive numbers into your memory. What this does is if you have, say, a negative 10 that comes out of... Well, okay. Just kidding. You can't have a negative 10 coming out of a hyperbolic tangent. If you have some negative 0.5 coming out of the hyperbolic tangent, and your remember gate says, okay, sure, I'll let that through. Remember gate outputs a 1, so you take 1 multiplied by your negative 0.5, and then you add your negative 0.1.5. add your negative 0.5, and that will give to you here in the memory a negative number, or will decrease a number. The reason it's a hyperbolic tangent instead of the sigmoid is so that you can decrease values instead of just only increasing them. It gives you a bit more expressiveness. You can have negative values as well. Does that clarify things a little bit? Awesome, yeah. And activation functions often, they're a little loosey-goosey. They get traded around a lot. But yeah, when you want a negative value, you probably want something like a tan h. When you want a 0 or 1 value, you want a sigmoid. When you want something that's just not negative, but it can be as big as it wants, then you'd use a rectified linear unit, our ReLUs from earlier. Awesome. Yes. Yeah. It's all good to normalize things. That way your output's always in a sensible range instead of like 8 million something. Cool. All right. Are there any more questions? I guess I should look at the poll again, see how people are doing. Okay, we've got 6 people who are feeling good. Well, 5 people, I guess. So, awesome. I will interpret that as most people doing all right. If you have other questions, fire them at me anytime, and I will try and jump and take a look at them. Cool. Well then, let's get to actually implementing some of these networks. Hopefully this will be a much more engaging part than we were at just a minute ago. But I think some of those fundamentals are good to understand, because otherwise it just looks like I'm typing letters. You know, I'm saying, oh, add an LSTM here, and you might be like, what in the world is that? Now at least I guess you know where you can find that kind of information and have a basic idea. So I think it's nice to have that sort of understanding. Cool. All right. We'll start then by importing the work that we've done last time around. So in our pre-processing file, which is here, remember, well, or maybe not if you missed last session, which is totally fine. Basically what we did is we found a way to, and I'll actually go, yeah, we're already there. Our data folder here, data final, we have a bunch of EMG data. Each one of these different files is a different gesture. And inside of each one of these is a whole bunch of repeats of that gesture. So that's me doing the gesture over and over and over again. So we can have lots of statistical significance. And what this is all doing is loading all 8 of those files into one nice big data frame, which is like a spreadsheet in Python. And then the shaping of ML data is producing the inputs and outputs for our neural network that we'll need exactly. So we'll import from there, from pre-processing import, a couple of functions. First one is the one that loads the EMG data. So load EMG data from folder. And then our next one is shaping the machine learning data. We don't need this read repeats because that's only used by the load function. So we don't need to load individual repeats. We're just loading all of them at once. Cool. Okay, so we have that. Let's actually do some loading of things. I'll create a variable called data. And inside of our data, I will load the EMG from folder. And the folder, as I just showed here in the File Explorer, is data/final. So we have data/final. There's our data loaded. And then if we want to shape the ML data, so we have inputs and outputs, I could have the EMG tensor. So that's the input. And then we have our labels, which are our gesture labels. So labeling this as gesture 1, or this is gesture 5, or gesture 7, or whatever. That's stored in the labels. And that is both coming out of our shape ML data function. So there we are. And yes, just remember the way that we can do these double variables output is because we're returning a tuple, the first of which is the data from the EMG column here, the second of which is the data from the gestures. So there we are. Lovely. And we can go ahead and run that, take a look at our variables we get. Et voila. Just as we saw last time, we have our nice data frame here for data. Well, actually, I can use Spider properly this time because I fixed the scaling of it. Well, kind of properly. So you can see there's our input data, very messy looking, but along the right side you can see the gesture number changes for the different gestures that we've recorded, which is quite helpful. So there's our input, and then our EMG tensor, same as what we looked at last time. Remember here that the shape means this is 231 repeats, each of which is 118 time steps long, and each one of those 118 time steps I've recorded data from 8 different EMG sensors. So that's where that shape comes from. Cool. All right. Now we can build a neural network. Which one do people want to build first? Do people want to build an LSTM or the convolutional neural network first? Any preference either way? CNN or LSTM? Dun, 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 dun. The crowd is contemplating. CNN is pretty good. Yes, convolutional networks first. Excellent, yes. Cool. All right, so yeah, I think that's a good idea. We can take a nice look at that. In that case, we will define a nice little function here for def build of a convolutional neural network. Let me know, by the way, if any of this is small. The scale is smaller than last time. I think it's all right, but if you have a small screen, let me know and I can try and make it bigger. And for our convolutional neural network, it'll be helpful later on, or now-ish, to know the input shape and the output shape. So here, what each of these would be, the input shape is going to be our 118 by 8, because that's our time steps and sensors. And the output is just going to be some number 1 through 8, because we have 8 gestures to categorize. So there we are. Cool. Build the convolutional neural network. Right, so this one's slightly more complicated than the LSTM one to build here. And I'm contemplating doing the LSTM first just for the sake of example. And I'll throw all of the democracy that I asked for a second ago in the dirt. In fact, I think I might do that. Don't worry, we'll get to the CNN very soon. I agree, I like CNNs way better. They work way better for this problem. They're like 10 times, well, spoiler alert, it's like 10 times faster and it's better at categorizing things than the LSTM is. But we'll start with this one, just because it's easier to write. So we're just creating a local variable here called the model. And this will be a sequential model. So TensorFlow gives you a whole bunch of different ways to make different machine learning models. As a quick peek, we have, there we are, I think. Yeah, so there are 3 main different ways to create them. The one we're going to be using is the easiest one, which is the Sequential Api. So this is just like the convolutional neural network that we looked at, where you have layers in a row, like this. It's a good question, Ben. I'll come on to that in just a second. We'll have things like this, where they're just stacked up. It's totally linear. It's sequential. So that's this easiest Sequential API. That's the one we'll be using today. But just know, if you're looking for something fancy, like with branches, like this one has, so you're having an input layer that's going into 2 different layers, and then somehow getting combined or something, you can do that as well in Keras/TensorFlow, and I'll talk about the difference between those in a second. Or you could get even crazier and do some inheritance. If you remember from our object-oriented session, you can inherit the model class, and then you can customize every last bit of the model. You can manually write how it's trained. You can manually write how the outputs are calculated. That's the most power, hardest to use, easiest to use, least power. But for us, sequential is more than enough, so that's what we'll be using today. So just know this sequential thing means one after another steps, layers without any branching. To answer the question that Ben asked, which is what is the difference between Keras and TensorFlow, there used to be one. It used to be that TensorFlow was the base library that did like the maths for you and optimized all the neural networking stuff, but Keras was what gave you the easy to use layers, like we'll be seeing in just a second. But as of TensorFlow 2.0, which I think, well, let's Google it. I think that came out a year or 2 ago. So TensorFlow 2.0, when did that exist? I don't really know. TensorFlow is now available, so that was 2019. So since 2019, TensorFlow ate Keras. So Keras is now part of TensorFlow. It's a subpart of TensorFlow. But the Keras bit, it still retains kind of its original purpose of Keras is the really nice, easy to use stuff. So if you're just trying to solve problems, Keras is where you'll go. If you're trying to do original machine learning research and invent your own layers and neural network models, then you'd just be using TensorFlow. You probably wouldn't be too fussed about Keras in particular. Does that help clear up the distinction between the two, Ben? Awesome. Cool. Nice. Yeah, so, yeah. In fact, speaking of which, I need to import from Keras and Tensorflow for that sequential thing to work. You can see there's a little error there. It's complaining. So from, and here you can see exactly what I just talked about, the combination of the two. Tensorflow dot Keras. Wow, look at that. It's inside of each other. Models. And the model that we want to import is the sequential one. So sequential. Excellent. So sequential model is imported. And then some other things that we want to import are some layers to work with. Like I said, it has these like layers for like convolutional neural networks all pre-baked in, so you don't have to worry about it by hand. So that is instead being imported not from models, but from layers. And from layers, we can import all the ones we'll need for a convolutional neural network, which are the convolutional one-dimensional neural network, because we're going just one dimension over time. We don't have a two-dimensional image here. But I think they have two-dimensional ones. They might even have three-dimensional ones. Do they have three-dimensional ones? They have three-dimensional ones. Do they have four-dimensional ones? No. Okay, it stops at 3. But you can write your own if you need four-dimensional data somehow. We're using a one-dimensional one because our one dimension is just time. And then another thing we're going to be using is global max pooling. So remember from our pooling layers, these are things that just kind of downsample our input. They look at a big area, and they just give you one output for that area, then they move into the next area and give you one output for it. What this global pooling does is instead of having 4 things like this, global pooling simplifies things even more. It says, what is the biggest number in this entire set? Hey, look, it's 8. There's your one output. The way that doesn't throw away all of the information on the network is because, remember, these things, this is a single depth slice, like it says there. But these networks can have some depth. So if you look at something like here, where this green output has a depth to it, it will still retain all of the depth. It just gets rid of all the width and the height. So you can imagine here, doing a max pooling, it finds for every single one of these values in here, so say there's, well, it looks like there's 5 values here, so 1, 2, 3, 4, 5 values. For each of those 5 values, for this first one, it would look down here on this first row, and would just pick the biggest number out of this width and height. For the next one, it would pick the biggest number out of the height and width for the next one up. That kind of thing. So that's how global max pooling works. And we'll be using that as part of our model. And then the last thing we'll need is a fully connected layer, or the feed-forward neural network, or, as TensorFlow calls them, all the same word, or all the same meaning, a dense neural network, or layer. Excellent. That's all the imports we need there. And now we can make our first convolutional thing. Awesome. So we will start then by taking, you can add a layer to a sequential model just by doing model.add. And then inside of the add, you just give it the layer that you want to have. So our first layer is going to be a convolutional layer. It's going to be our one-dimensional one here. And then we can give it some parameters. In fact, we have to. So as it says here, very helpfully, thanks, Spider, the first thing it's asking about is filters. How many filters are there? So if we go and take a look at our thing here, the filter number is how many features you're calculating. So you can see as this goes along, hopefully. Yeah, there we are. Here it's calculating that second filter. Here it's calculating the first filter. And you can see that's giving these different outputs. And they're different. This is what can create the depth, if you will. So if we're scanning over up here, this input, here, from our first to the second layer, we must be increasing the number of filters because the depth is growing from, like, say, the 3 that would be the color inputs. So here, these numbers, by the way, that I'm going to be putting in have been kind of determined via trial and error almost. There are good ranges and bad ranges, and there's some ways to make like educated guesses about them, but tuning a neural network, which is actually something that's the entire theme of basically the next session, is a pretty complex and more artsy than sciencey process, which upsets me, but hey, the way the world is, I suppose. Not everything has an easy solution. Cool, so our filters, I'm going to start with quite a few different things. We're going to start with 128 of them. So that means we can pick up on like 128 different little features. The next part is the kernel size. So the convolutional kernel is the same thing as like the filter size in 2 dimensions. So, boy, I love scrolling on this web page. So, for example, here, these filter sizes or kernels, they're kind of the same meaning, are 3 by 3. So you can see 3 by 3. So what we want for this first one is actually something a bit strange. So I've shown you how here the point of the convolutional neural network is you have these big filters that you can scan over so it can look at the interactions between a bunch of different things in an area. For us, this one dimension, in fact, we can go back to the one-dimensional example, this one dimension might be time. So you can imagine, if we're just looking at one time step at a time, that's probably not terribly useful, right? Why would we bother doing that? Well, the reason we're going to just look at something with a kernel size of 1. So here it's a kernel size of 3. It's pointing at 3 things. Kernel size of 1 would just be pointing at 1 input. The reason we're doing that is because, again, they have depth. In fact, ours are 8 deep because you have 8 different channels. So if we have a kernel size here of 1, what that does is it doesn't look at any of the time data yet. It just looks at each time point in isolation. So it can't figure out time patterns yet. But what this will do is look at the patterns between these different EMG sensors. So this will learn the spatial information from the EMG band and tell us, okay, when sensor 1, 3, and 4 are activated, this looks a little bit like this feature, and it can classify 128 different features. And then this information is going to be used by the higher layers that actually take into account time. So then those layers will be saying, okay, I know that at the last point in time, this particular pattern of EMG sensors was picked up, and now we're picking up a different pattern. That must mean this is happening. So this first bit is getting us spatial information on the Myo band between the different sensors, not time information yet. Activation here. Convolutional neural networks work incredibly well with rectified linear units, so ReLUs. And so that's what we will use. Again, that's a bit of a trial and error kind of thing, but convolutional neural networks in general work very well with these. They're very quick. And the last thing, since this is our first layer, we need to tell it the input shape. So this is what we're feeding into the network. So here we've described we want an output that is 128 deep, but we don't know the size of this image, say. So here, like where we have 5 dots, we have 128 of those, so it's very big, but we don't have any idea how big our input is. So we don't know if it's like 32 by 32, or in this case, like 118 long, because that's just the time information part. 118 by 8, I guess, because it's 8 deep. So we can give it that input shape by passing along that parameter. We'll see how to calculate that in a second, but just in shape is what we're passing along there. Cool. Then we can vibe along. Also note here, we don't need any padding because we're not doing any spatial things. It's just one input equals one output. So like one time step will generate one time step out. In fact, yeah, we'll need to generate a little bit further. You'll be able to see this in a minute. This whole, how the shapes change as we go through. Cool. So now we'll add our next layer. My next layer in the model that I put together is another convolutional layer, but this one's doing some spatial stuff. So this next one, here I'm reducing the number of features. So I'm taking it down, instead of looking at 128 different patterns, let's only look for 64 general patterns. And out of those 64 patterns, I'm going to have a kernel size of 3 now. So now we are doing exactly what we can see here, where I am looking at, there's the previous time step. Here are the spatial patterns picked up. Here's the current time step. Here are the spatial patterns picked up. Here's the next time step. Here are the spatial patterns picked up. And this neurons can take all those different spatial patterns, combine them with this time information, and generate us some new higher order features. So now we have a kernel size of 3. I'm going to keep the strides just regular, so it's still going one at a time. Because I don't want this to shrink yet, I'm going to do that thing that I talked about earlier, where it's padding equals same. So this is going to add some nice little zeros around the outside of our convolutional neural network, so it doesn't cause any issues. So it'll add all these zeros along, so we can get the same size output as input, while still scanning this kernel size of 3 along. So this is pretty close to what we'll be doing, except we'll be doing this in 1 dimension instead of 2. Awesome. And then activation function again should be a ReLU. Activation ReLU. Beautiful. That is that layer done. Then we can have another layer I've added in mine. Again, it's part of this is very art, not necessarily science, so you could write things very different from this that still work very well. I've reduced the number of features again, and I'm going to once again look at different space patterns. So I'm going to go up to a kernel size of 3, looking at time step before and after and the current one at the same time. But now what I'm going to do is add a stride. So strides, and I'm going to do 2. So now we're really looking like this example here, where I'm jumping 2 at a time. So the output is going to be smaller than the input. So this is our first step of decreasing our big input, which is going to be 118 long and 8 wide, or 8 deep even. So it's going to take that big 118, it's going to make that much smaller. So we're starting to shrink it down, because we eventually want to shrink it down into something that's just basically 1 by 1, but with some depth, which is what we have here, for example. So we're shrinking it down. So the strides is going to help with part of that. We're going to keep the same padding and ReLU stuff from earlier. So those features go unchanged in this layer. And then finally, we've downsampled it a bit. We've gotten down to 32 important features. So these 32 different things are identifying a combination of spatial patterns from the first layer, a combination of time patterns from the second one, and then a combination of time patterns on this layer. So you're kind of getting a real good picture of what's going on. And then what we're going to do here is just, okay, I don't mind where these features happen. I don't mind if this gesture happens at the beginning of the time period or it happens at the end of the time period. Hopefully we're picking up a gesture here. Just give me the most prominent gesture. So we can do that with our global pooling layer. Global pooling layers are very easy because what they do is so simple. There are no parameters. Just that, and you're done. It will find the most significant features out of all of the space that's left here. And the final thing to do, and this is the part where we're turning this volume of information here, this volume of little features that we've picked up in the time frame, and we're going to turn those features into the probabilities that it's different gestures. So to do that, we're going to add on one last layer. That is the model dense layer. So here's our fully connected network at the very end. So this is following the same architecture that we see here. It's got a fully connected layer. Remember, these dense networks look a little bit like this, except in this case, it's going to have 32 inputs and 8 outputs. So imagine 32 inputs and 8 outputs. Awesome. And here, we give it the number of outputs is the out shape. So I want 8 outputs out, but we'll see that in a minute as it's passed in as this variable. And the very last thing we want to do is give this a different activation. So this activation, welcome to a new activation type that we've not talked about before, softmax. This one's really cool, actually. I quite like this one. What softmax does is something much more complicated than the other activation functions. This can turn any bit of, I think they're called logits. So the output that you get from a dense network, for some reason they've called them logits, like logic bits or something. But what this does is it can turn any set of those numbers into a probability distribution. And I guess I can show you exactly what that means. So softmax. There we are. So yep, it turns arbitrary real values into probabilities, which are useful. And it does this by calculating the exponent of each thing, using e as the natural base. The reason it's doing this is so that everything is a positive number here. So you can see, for example, I need to zoom in on this a little bit, probably. Wonderful. So you can see, here, if your input is a negative number, you're still getting a positive output, which is nice, because regardless of what these values are, your probabilities can't be negative. You can't have negative probabilities. Probabilities have to be between 0 and 1. So it's a bit like a sigmoid in that it squishes things between 0 and 1. But instead of just pushing things between 0 and 1, it also keeps in mind the relative sizes of these different things and calculates the relative probability for you. So here you can see that exponent bit here is pushing it between 0 and 1. But on the bottom, this fancy notation just means you're summing, and like it says here, you're summing up all of the exponentials for all of these different powers of e on the bottom, so all of your outputs. So, for example, here your numerator is e to the minus 1, so e to the minus 1 is equal to that. But your denominator here, well, actually it's shown here, isn't it? Is just the sum of the e's of all of the other values, including this value. So you're taking the -1, 1, you're taking the 0, 1, the 3, 1, and the 5, 1. You're getting that. So it tells you what proportion. So it scales this to be a proportion of the total probability. The nice thing about this mathematically is that all of these here add up to 1 on the very end, these output probabilities. So the output of softmax is always a probability distribution, and if you integrate the whole distribution, you get 1 out of it, because 1 is certain. So you're certain to have one of these things happen, and this tells you that 5 is the most likely, or that, yeah, this output is the most likely, this one's the next most likely, then this one, basically. And so that's a really nice activation function that instead of just processing one value, processes all of the values at once so it can scale them to be a distribution. We'll be using that because what we want out of it is a probability that it is one of the gestures. So we have currently an output that will say, here is each one of the gestures, I've given it a number, but what we want to do is turn all those numbers for each of the gestures into a probability that each of those gestures is happening. So, softmax will do that, and then we can finally compile our model. So this means you're putting it together, you're giving it the last little bits of information it needs to function. So remember earlier we were talking about loss functions. Loss functions are what you want to minimize. So for different problems, you want to calculate your loss in different ways. That example that we looked at, the very simple one, used a mean squares loss, I believe. Not that I remembered where that was. Here it is. Yeah, so it used mean squared error loss, which is this calculation. We want to use a different one because it's not really that there's a correct answer. We don't want to, because we're dealing with probability distributions. We don't have one number like they had one number. So to deal with that, there's something called categorical cross-entropy. It's really kind of wild, so I won't dive into it too much, because the entropy thing refers to information theory. I've included some links that you can look at. It's like, what is information entropy? And I'll include this in the little bit of links I sent out. But it's talking about, basically, the bit of it to take away is that, and it doesn't even say it. Oh, there it is, yeah. If something is a low probability, it's high information. So it's important to, I guess, keep track of or whatever. And if something happens all the time, it's probably not as rich in information. So what this is basically doing is calculating the difference between two different distributions of probability. So here, there we are. Two different probability distributions for some random variable. So you can see by I, these look very different. But how do you quantify how different they are? Well, you can use cross-entropy. So you go through the calculations for it, and you'll get things like, and the units is in bits, or sometimes in nats, I think if it's natural bits or something. Nits, maybe? Terminology escapes me a little bit. But the idea of this is, if you have the way that this is calculated, let's see if I can find the equation. I just realized lots of that was probably a bit small, but that's all right. The core is just to take away what it does, I guess. So here, y is our one hot encoded yes, no, is it this gesture, is it not? So this is the correct answer. Our prediction, we put through a logarithm. Here, it's the natural log. I know that they've written log and not ln. That's because they're pretending that it's real maths, but they're being bad at conventions. Anyways, this is log base e, but it can be log base anything, basically, with the way this works. And you're just seeing, okay, if this value should be 1, so if it is this gesture, you're calculating how far away are you from this gesture on a logarithmic scale. And you're doing that for all of the gestures, which is what the summation does. Not vital to understand that 100%, because in TensorFlow, for example, the loss function, when you type in its name, you start with categorical. And that is because we are dealing with categories. There are a couple different categorical things, but the most popular and the best functioning oftentimes is this cross-entropy thing. which you are certainly free to look into more, and I can send the links after. Cool. Cross-Entropy is our loss function, so that'll tell us how far is our probability distribution from the other probability distribution. So, oh, I've lost which tab it was in. Oh no. Yes, here we are. So it tells you, it's a way of quantifying that these are very different, and that if they looked identical, then they'd be very close. So that's our loss function. We want to make the inputs look as close to the outputs as possible. And they're both probability distributions, because they all sum to 1. Cool. Categorical cross-entropy is there. And then we'll take then we need to pick an optimizer. Cool. Yeah, so I think we might have to, that's actually all right. So I think since we're running a little bit low on time, I'll continue to explain things as I was planning to, but I think since it'll take longer than the time we have, what we'll do is maybe push our, oh, I just realized we're building a CNN. Wow, that's fascinating. Remember when I started this and told you all that I would be switching to the CNN or the LSTN and then didn't do that? Anyways, been a long day. Anyways, we are building the CNN. This is the more complex one. The other one's way simpler. That's right, this is good to get out of the way. Yes, so since we're running a little bit low on time, I'll continue forward with this. Our next session may need to include a little bit of the LSTM, which will be nice and simple, and we can compare the LSTN to the CNN. That'll be the main theme of that session. But we'll power forward for now. Cool. Okay, so our optimizer. Adam, what does that mean? Well, this is the last little bit of yeeting off to a website that we need to do. So remember from our original machine learning thing, we were talking about how you actually train these neural networks, that we need to minimize this loss somehow. Well, it turns out there are different ways to do that. That's what optimizers do. So what we did in this particular example is we just did the simplest possible thing, which was stochastic gradient descent. I think they said that word somewhere. There we are. Stochastic gradient descent. That's what this equation is. So remember, this is the gradient, so the effect that W has on the loss. So we want to change W so that it reduces the loss, and we multiply that by this learning rate. That learning rate is always fixed in this particular model, so it's always the same number. So we're always making the same size jumps, if you will, from one learning cycle to the next. The problem with that is sometimes you want your learning to slow down as you get closer to the correct answer, so you don't overshoot it. Because if you overshoot it, then you're going to end up with some issues. So that's why lots of these other models have been developed much fancier than just this. But even this gradient descent can be done in some different ways. So, talking about gradient descent. So the one that Tensorflow does is actually something called batch gradient descent, which is a hybrid between stochastic gradient descent, which is the example here. This is just using a singular sample, I guess, so a singular loss value for a singular weight, instead of going through and calculating it for every single bit of training data. So this calculates it from one training example, not all of them. The other way to do it is by doing all of them. I wonder if it talks about that. Oh, that's what batch is, sorry. So we're doing a mini batch, actually. So batch will do this gradient calculation, except it'll calculate its gradient for every single input that we're giving the network. So say if we're giving our network, in this case, 231 different inputs, it will run this 231 times and find the average change, and it will make that change. So that's giving you the optimal, moving down the network or down this gradient in the best possible way. But this takes a long time computationally. So stochastic gradient descent is, so that is this here, where you're calculating the overall gradient. But the stochastic gradient is just using one sample of data. So you're using one training example. So instead of using 231 repeats at a time, you're using one repeat at a time. That's going down. So it's much faster and often used. But you can see here from this graph, which I will zoom in on, it can sometimes learn a bit janky like that. Because if you imagine you're just looking at one example, not all of your examples at once, sometimes what's good for one example, so if you want to improve the classification of one example, maybe that was a bad example. So it's made the rest of your good examples now look worse. So that's what you get when you have these big spikes here, when it gets worse, but then it gets better, and then it gets a bit worse, and then it gets better. But generally, this is a plot of the loss function. So you see the loss starts really high and it goes down. So you're minimizing the loss, but it's a very bumpy path with stochastic. And then mini batch that's what the one that TensorFlow does. So sorry for the confusion earlier. It takes the best of both worlds, like it says, and it does this batch thing where it calculates all of them except all of them for a subset. So we'll see that in our batch size parameter very soon in TensorFlow. So it can find a better direction than just picking one example, but it doesn't have to look at all of the examples. So it's faster, but also less spiky and irregular than this is. The way that something like Atom improves on that is using a couple things. The first thing it has is momentum. So if you think about this, imagine this as a ravine. So this is like a topological graph. So the center ellipse is the lowest point in space. And then this is one more space step up. This is another space step up. This is another space step up. So it's our job to move this loss. This is the loss function. We want to get to the lowest loss possible, which is right in the middle of this ellipse. If you start here, since it's really steep, you'll be pushed over to the other side of the ravine. And you'll kind of ping pong back and forth, and you'll gradually get closer to this middle loss part. But what momentum does is it's just like in real life, I guess, with physical objects. It says each time you update, don't just update based on the thing that we've calculated from gradient descent, but also remember the last movement that we had. So here you see there's this really big movement to the right. So it means that this next movement is going to have more of an influence pushing it to the right. So you can see that's how this one has a bit of momentum going in here. Bit of a tricky concept to understand right off the bat. But the idea is that can help you converge on a minimum faster. So Atom includes that part of the way. And the other thing that Atom does that's really clever is it combines. This is a really thorough article that I spent a bunch of time going through this morning, but it's not all vital. The other thing it does is it gradually slows down the learning rate. So remember how I said that in like our example here, this nu is a fixed learning rate number. So sometimes you're updating things too big, so you're ping-ponging around your local minimum. So say, if you had a constant updating rate, here's the minimum that you want to get to, but your update rate is really big. So you start here, you ping pong way up here, and you go way down here, then way up here, then way down there, and you just kind of ping pong back and forth over the minimum, but you really want to be in the minimum. So you need to decrease your learning rate so that you ping pong, but you kind of slow down and you eventually settle in the middle like that. So that's the other thing that this algorithm does. So it combines the best of these both worlds. It has a bit of momentum calculated in it, but it also takes from this RMS prop thing, which reduces the learning rate based on the squared or the average of the last updates. So if your last updates were smaller, or your last gradients were smaller, then this next gradient is also going to be smaller, or the learning rate is going to be smaller. So it combines the best of both of them. If you're interested in the maths in general, look at this. As a blanket rule, probably just use Atom for everything, unless you have a reason not to. At least at the moment, it's just about the best thing that we have in terms of optimization. It learns very quickly and without too many issues. So optimizers basically tweak that gradient descent process that we talked about at the very beginning. And this tweaks it in a way that makes it pretty quick. Why is that red? Invalid syntax. Well, I'll find out what's wrong there in a minute. I don't think anything is. That's fine. Cool. So that is that. Anything left to do? Oh, yeah. If we want, while we're training, to see the accuracy of our model, we can add an extra metric. So by default, it'll show us the loss of the model, and we can watch the loss going down, which is always really nice to see, because that's the point of training a model. But we can also look at the accuracy, which is how many of, like, the percentage of things that it's classified correctly. So we can look at that as well. Then from our function, finally, we can return the model and use it to actually train. So in training our model, first thing we want to do is split our data into training data and testing data. So at the moment, EMG, tensor, and labels, those contain all of our data. But when you're training something, and I mentioned this a bit last week when Kate asked a question about it, you don't want to train on all of your data, because then you run that risk, even if we're doing things like max pooling and our strides here, you still run the risk of like kind of memorizing the data set. So you want to be able to test your network with data it's never seen before. So for that, there's a nice way to split your data into testing data that it's never seen and training data that it's going to get better by looking at. And that's with a function actually from scikit-learn, which is yet another library. But luckily, you don't need to use it with scikit. You can use it with anything, as we'll be using it with TensorFlow. So sklearn is scikit-learn. And then it is model selection. That's the module. And we want to import from there the train test split function. Then what we can do, this is another function a bit like our shapeml data that outputs several things. This will output several things, except this outputs a load of them. Outputs 4 of them, I think. First, it outputs the X training data. And X is our like inputs here. So think of those as inputs. So that's going to be the EMG tensor. And then it also has your X testing data. Then you switch it with Y training. Yeah, Y train, and then Y test. Just like that. Then you just feed it in to this test train split function. And this does, oh, well, there's your documentation. I didn't mean to do that. But it's very nice for several reasons, because not only does this split your data by a certain percentage, so you can say, by default, I think it is, well, that's a good question. By default, it's set to 25%. So 25% of this data, of our data, so 25% of 231 will be turned into testing data, and the other 75% is training data. You usually want your training data to be bigger, because the more training data you have, the better your model. So here we are, test train split, and then we just feed into that our X data, which is our EMG tensor, and our Y data, which are our labels. So those are our correct answers there. Lovely, that'll plop those out. Then the next thing to do is finally, we can build our model. So our model variable, we can build a CNN, which took us a while to do, and our input shape and our output shape. Like I said earlier, our input shape that we're feeding into this model is going to be our 118 by 8. So we could just write in 118 by 8. That's a bit non-ideal, so we can calculate it. So that way, if this updates in the future, we won't break our code. So EMG tensor shape. In fact, I can show you what that looks like. Just copy it over here. That's this value up here, the 218.8. If I just want the second 2 bits of it, I can slice it. Starting at the first value, which is, remember, or first index, which is the second value, so it's starting there and going to the end of it. This will give us then just those 2. That's what we want. That's our shape. That's our input. And our output, remember, is just 8. We could type just 8. It's probably better if we get 8 out of the label size. So here it's currently 231 by 8, so we just want to grab the index 1 value there. So we'll do labels, shape, first index. That will give us our 8, as you can see there. 8. Wonderful. That'll build our model. Fantastic. Finally. And we can look at a summary of it. Let's do that real quick. Summary of the model. Yep, that'll do. There we are. Go ahead and build it. Invalid syntaxes. That's fine. I forgot a closing bracket. That's what it was complaining about. Another bit of invalid syntax. Did I forget a second closing bracket? No, maybe not. Let's see what it whines about. Metrics accuracy. I forgot a comma. Comma at the end of optimizer, of course, because this is still part of the same function. You could write this like this, but that flows off the screen, so I put it on the next line. But it means exactly the same thing, except for the fact that that just auto-completed something terrible. There we are. Beautiful. Run that. Valid argument in that. That's because I spelled optimizer in the British way, but TensorFlow, of course, uses American English like everything does in computer science. I should have known that. There we are. Aha. All right. So what summary has done is shown us our network. So we can finally take a look at all those things that I was promising you were happening here. We can see them actually kind of happen. Our first layer outputs something that is the none, by the way, here. That means that it works for any number of samples. So the none, you can substitute for 231, or since we're going to be training it, 173. That number is what goes into the none. None means it can vary. It can change. But it's always going to take something that's 118 long, which is how long our EMG tensor is, and it's going to take in those 8 columns, and it's going to turn them into 128 features. Doing that, it takes 1,152 parameters. So this is our thing earlier that, remember, in our very, very simple neural network, this crazy simple one here, we had only a handful of parameters, like 1, 2, 3, 4, 5, 6, 7, 8, 9. We had 9 parameters there. Now, this first layer has 1,152, so obviously many more. Next layer is even bigger. This one is doing the actual convolving of things, so it's going across it. But here, because I have padding and I have a stride of 1, that's the default, you notice that the output size is still the same time length, it's still 118. But we've now looked at the adjacent features using our stride, or our window kernel size, rather, of 3. So we've looked at the time steps before and after, and we've reduced our number of features down to just 64 features, but now these features include time information as well. And then finally, we've gone and shrunk down the size by doing some strides. So these strides are essentially going to like almost halve our data size. In fact, here exactly halve our data size because we're jumping 2 at a time. So we've reduced the number of time steps down, we've shrunk our features even more. And then finally, with these 32 features that we've collected, which have time information about time information, so that's double time information, and then also spatial information. By the way, the stacking of this time information allows you to see, if you imagine a bigger umbrella of time, if that makes sense. So let's see. There we go. So here's just one layer. But if you can imagine this 3, if this 1 here was also connected to 3 at the bottom, there and there and there, then you can imagine that this 2 actually has information from not only 1 space away, but also from 2 spaces away indirectly. So that's how stacking those time layers allows you to look at larger regions of time. So one of these things is now going to look at a big umbrella of 6 or 5 values on the bottom at least. So you can see bigger slices of time, even though we're only doing a kernel size of 3. It's seeing more than just 3 time steps at once. Then max pooling is happening. As I told you earlier, that takes our 32 features, keeps our 32 features, but totally nukes the time steps. It's just one step in time we've looked at through the whole time step, just picked out the biggest features. That's what we got there. Then our dense layer finally takes those 32 inputs, turns them into 8 outputs without many parameters. And then we get something out the other end. What do we get out the other end? An excellent question. Let's actually train the model. So that's the last thing we have left to do. So in that case, we're going to jump. Yeah, I'll just replace the summary actually with fit. So you can fit your model a bit like you're fitting a curve or something here. And let's think what we want to put into this. We obviously want our data. So we're going to do our training data. So x train and y train. Then we can put in epochs. So the number of epochs. So this is how many times it's repeated. So actually, you know what? I'll keep this at 1 first time around. So we can take a look at it. Our batch size, I'm going to put in as 32. Now, actually, when I say put in as 32, I'll probably leave it out, actually, because by default, the batch size is 32. So that means it's when it's doing the gradient descent, it's not looking at all 173 of these values. It's not looking at just one of the 173, but it's averaging 32 of them. So that's what that batch size means. But by default, it's 32. We'll explore how changing that affects things more in our next thing that we do, our next session. But here we go. If we run this, wow, it's gone and done some training. Oh boy, it's gone through all of our data, and yet the loss is a massive number of 72, and its accuracy is only 20%. Terrible! But don't fret. It's supposed to be the way that you get these models better. It's not one look at the data that they'll instantly memorize everything. They have to see the data a couple of times over, so they gradually home in on something. So that's what happens with epochs. Epochs is how many times you pass over the data. So here, note, because the batch size is 32, 32 goes into 173 6 times, or actually 5 times with a bit of a remainder, but it does 6 batches to go through the data once. So this is 1 epoch. If we want to go through the data 15 times, we just put 15 epochs. Et voila. Zoom learns really fast, and by the end of it, because I told you this network is stupidly good at this, like that time that's just passed there instantly, it's got 100% of the training data classified correctly. But remember what I said, it could just be memorizing things. It could be totally, BS. So we got to make sure that it's not. To do that, I'll go ahead and copy a string. I don't know why I bothered copying this one. Just saying that this is just marking off the final result. That's just printing so we can see visual separation. And we can use a different function called model evaluate. And we can evaluate our X testing and our Y testing data. So note this is totally different data. We trained our model on Y train or X train and Y train. We're testing it now on data it's never seen before, which is the point. So if we test it on data it's never seen in the world before, we're gonna get zoom some outputs here. So you can see that even though I'll make that a little bit bigger. Just kidding, I cannot. I don't know why that's not fitting on now. Oh, it's because the loss has gotten so small. That's hilarious. Because the model's working so well and the loss has gotten so ridiculously small. It's pushed off our accuracy. But you can see on the training data, it's getting 100% of the training data classified correctly. But when we try it on the testing data, which it's never seen before, it's still doing incredibly well. 98% of the samples it's looking at out of, and that's a pretty big sample size, out of these 58 samples, 98% of them were classified correctly, which is pretty impressive. And you can see like the loss here is a bit bigger because it's never seen its data before, it can't memorize it. So you can see here it was definitely starting to memorize the data because that loss got so low. But here it still managed to remember the big general patterns. And so we've got 98% of our data classified correctly. We have 3 minutes. So just as the final thing, and this is me plopping in some little evaluation code. This is kind of something that we'll be looking at more in our next session. To quickly explain it, this changes it so that NumPy stops printing the scientific notation, because that annoys me a little bit. And it's nice to look at when it's not like that. I'll talk about what dstack does next time around, but it basically puts these two values next to each other for the data that it's predicting from this test data. So that's a model predict. Again, we'll talk about that. That basically does model evaluate, but just with one input. So if we give it this one input of testing data, what is the output that we're expecting? So I'm just going to line those two up side by side so we can visually look at them and see if they're checking out. So there we are. Well, that's a bit unexciting because it's so ridiculously good that there's hardly any loss there. Let's train it for fewer epochs. Move down to 5 epochs only. Really? It's still getting there after 5 epochs? Good lord. This network is too good to show anything useful with. I should have started with the LSTM. That is crazy how fast that converges on answers. It's very certain about its answers, isn't it? If I choose just one network, is it going to give me something a bit more interesting? A little bit. Okay, so here at least we can see it's pretty not great. We're down to only 30% accuracy. Here are the expected values, expected outputs. So this means that it's not gesture 0, 1, 2, 3, 4, but it is gesture 5, because that's where the 1 is. And here's the probability distribution. So this one, you can see it got wrong, because it guessed it's probably gesture 6, but it's not, it's gesture 5. Here it's saying it's probably gesture 3, I guess if the first one's 0, but it's not, it's gesture 6 or whatever, so it's misclassified that one. And it's also misclassified this one. So in this case, it's gotten all these examples wrong, but that's to be expected because the training was only 30% of them were correct. If we increase our epochs back up to the number that trained it really well, like this, zoom, now we can see expectations line up with what we want. So here, it's pretty certain that the correct answer is the correct answer, and it's right. Here, oh, fascinating. That's one of the ones that's misclassified. So that's kind of interesting. So 93%. So this must belong to the 7% of examples. It thinks that it's this one up here, but it's not. It's this one down here. And you can see its second best guess would be this one, but it's a far second. Then this one, again, it's correctly classified. that brings me with 7 seconds to spare to the 2 hours of time. So I certainly felt that this one got a little bit rushed at the end, but I'm around for as long as people need. Time for a gigapoll. For how are people feeling overall about applying things in TensorFlow? And next session will be showing off the Lstm, which I didn't have time for today, and also looking at how we can compare which ones are better, which ones are worse. Any final questions? Because I flew through this, so I'm here to answer any question whatsoever. It doesn't even have to be related to this code. Anything talked about today, anything machine learning in general, I'm here for questions. So anything that people have? I guess I can do a poll for... Yes, so the links to these articles, yes, I will be sure to post those. So you will have all of those as soon as I put up this recording as well. Awesome. I'm glad that was clear. It felt very waffly and pretty quick, but hopefully the combination of the links, yes, and the recording, which has been recording. Thanks for making me check. Yes, it should be pretty easy to go back and look at. Oh, and of course, if you missed the first session, all of this code I'm doing here, like this exact code, I've written just today. I spent too much time figuring out a good way to try and demonstrate things, but the code for our final classification thing, if you want to look at how the ARM team did this, our final goal that we're going for over the summer, take a look at this GitHub repository called Arms and Glory, part of the Sheffield Bionics thing. And in here, if you take a look at, and I'll zoom this in slightly for you. If you look at the preprocessing file, that's exactly what we've seen before. If you look at the neural file, that's our neural networks in here. So here we have our convolutional neural network, an LSTM. I also tried out one of those generic recurrent units, or it wasn't a generic recurrent unit. Whatever the recurrent unit was. Gated recurrent unit. Thank you. Yes, see, Ben's on top of it. I am not. Yeah, gated recurrent unit there. So there's that, plus all the code that we're going to be writing maybe next time around for evaluating things. So if you ever want to peek at these things, check out our repository. If you ever want to try writing it on your own, creating your own models that are better than mine, which I'm sure you can do, go to data, final, there you are. There's all of our data for you to download. You can just download it by clicking clone and downloading it there. Awesome. Cool. I'll create a poll for any final questions, just so I know. But otherwise, any final questions? Otherwise, I think that's about all for today. And next time we'll go over LSTMs really quickly and some other things that you can do with like evaluating your models. We'll dive into how this works a little bit more. I'll explain that. Yeah, and we'll talk about evaluating things and how you can improve your machine learning networks and decide which ones are improved and which ones are just random chance better. Because, for example, and here I am doing one last demonstration, but as the one last demonstration, if I run this once, accuracy is 93%. That's pretty good. Run it a second time, accuracy is 96%. Run it again. It's random every time. Like, it's within a field. Now it's 98, but it changes every time. So with that randomness, how can you be sure that something is better than the other thing and not just, chance? So that's what we'll talk about next time. Awesome. If there are any final questions, feel free to type them. I'm going to vibe here. Otherwise, have a lovely day. And I will see you next week. And I'll hopefully send out a feedback form because I feel like this went a bit fast. But the recording and links will all be up on the Discord very soon tonight. Awesome. Yes, thank you for coming along. Thanks, I'm glad it was hopefully a bit helpful. Cheers. See you next time. See you, Philip. Thank you for coming along. Oh, that's on the recording. Sorry for the death cry, people watching the recording. I'm just very exhausted. Hopefully the session was nice. See you next time.